by right. Does that make sense? It's not like videoing you. Whoa, I see you. No. Okay, so one-dimensional kinematics equation. So there are kind of two cases that we're going to deal with. Case one is when there is no acceleration. So that means that the change in velocity is equal to 0. In that situation, when there's no acceleration, the change in velocity is 0, there's one equation that is appropriate. And that's the one that we learned last time we were together, that velocity is equal to displacement over time. Okay? The only time that you can use this equation is if acceleration is equal to 0. The only time you can use this equation is when acceleration is equal to 0. Got it? Okay. Questions on that? It's really important. It's more fun when acceleration doesn't equal 0. So if acceleration does not equal 0, but is constant, then we have these four equations that are kind of fun. Okay? If acceleration is not equal to 0 but is constant, then you've got the one I'm going to call number 1, which is the one that we wrote down a minute ago. Acceleration is the final velocity minus the initial velocity divided by time. But if you look at your equation sheet, that equation isn't on the sheet written that way. Okay? The way it's written on your equation sheet is by having multiplied by time, and I believe that it's solved for VF. So it looks like this. VF is equal to VI plus AT. Some of you are algebra whizzes, and looking at that, you're like, oh yeah, I get that. For some of you, it might take a couple of minutes to kind of look at that, step back to see that these two are equivalent. Is there anybody that wants me to walk through and show you that they're equivalent? I'm very happy to. You just need to let me know. We okay? Okay. All right. So there you go. That's equation number 1. The second equation that we can use if the acceleration is not 0 but is constant, now we're going to start introducing more interesting things like delta x. What was delta x? The displacement, right? So we're bringing that displacement back in. This equation says delta x is equal to 1/2 v final minus v initial times time. I'm just going to keep writing. Number 3 is the one that looks perhaps the scariest from the beginning, but you will get to know and love. This equation is the one that you will use most often throughout this course. Displacement is equal to VI, so the initial velocity, times time, plus 1/2 times the acceleration times time squared. Yuck. Or, yes! That's a great equation. It's got so much information in it. Okay? Don't be scared by that squared. It'll be okay, I promise. And the fourth equation, again, as I said before, we can get these, like you can do the algebra. You guys have all of the math skills to get there. I just don't want to go through them all with you right now. The last one is VF squared is equal to VI squared plus 2A delta x. Those are the big four. Okay? So you may be looking at those going, wow, that's a lot of stuff. Do I have to memorize that? And the answer to that question is no. Remember I gave you that purple sheet? They're all on there. Okay? So you don't have to memorize them, but you definitely need to know how to use them. Okay? And perhaps more importantly, you need to know which one to use. It's not just like, oh, let me pick my favorite. There are certain ones that are better to use at certain times. You know what I'm saying? Okay? You got to use the right tool for the job. So, when I used to teach this class, I would just say, okay, go, and then we'd give a bunch of problems, and then students would maybe not start to cry, but maybe feel a little overwhelmed to go, oh my goodness. And so as a department, we figured out that this is a helpful tool. So I'm going to show you the tool that we're going to draw. We're going to draw ourselves a little chart. So on your paper, we want to draw ourselves a chart. It is going to have 5 columns and 6 rows. 1, 2, 3, 4, 5. Yep, 6 rows. And this handy-dandy chart will certainly come in handy, especially as we're getting started trying to figure out which equation to use. Along the top, I'm going to number the equations. So this is equation number 1, equation number 2, equation 3, and equation 4. And if you look at those equations, they all have some things in common, right? Or some of them have some things in common. What's one thing that you see in at least in more than one equation? Delta what? X. Delta X. Absolutely. Delta X exists in some of them, right? Does it exist in every single one? No. What else do you see? Besides Delta X, raise your hand if you can tell me something else that you see. What do you see? Velocity. Like what kind of velocity? Velocity initial and or final. So there's velocity initial and there's velocity final. What else? What else do you see? What else? Time. And there's one more. You guys, yeah, go ahead. Acceleration. So I just want to let you know, sometimes I see like the same people's hands going up and up and up, and I'm not probably going to call on you right after I just called on you, not because I don't love you, but because I want to share the fun, okay? I want lots of people to talk and play. So that's why I just don't want you to feel bad that I'm not calling on you multiple times. Okay, so let's do one of these together. I want to look at equation number 1. Does equation number 1 have a delta x in it? Take a look. Does equation number 1, that's this one here, have an x in it? No, it doesn't. So I'm going to leave that blank. Does equation number 1 have a VI in it? Yes or no? Yes. Does it have a VF in it? Yes. Does it have a T? Does it have an A? Yes. I would like you to go through equations numbers 2, 3, and 4. Oh, yeah, go ahead.
Is it a delta T or just a T?
You could write it either way. So delta T means a change in time. So that would be like I started my stopwatch and I stopped my stopwatch. I call it more just like how much time has elapsed, which would be the same. Does that make sense?
Okay, so it doesn't really matter.
I don't care. I think the book always uses delta T. I will almost never write delta T. Is that fair?
Okay.
Yeah. Either way is fine. Okay. I want you to go through real quick by yourself first, and then as a group, we'll look at them 2, 3, and 4. Go ahead. Okay. Let's start with that back table back there. Hi. What did you guys say for 2?
Delta x, VI, the velocity, initial velocity, final velocity, and time.
And time? So no acceleration, right? Okay, cool. Let's go to this back corner. What did you guys say back there? For number 3. Yep. Sorry, I didn't clarify. Everything except final velocity. Cool. And let's go to this table right here. Somebody at that table want to share? What did you guys say for number 4?
Everything except time.
Everything except time. So yes, 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 and there we go. Okay? So here's the deal. There are 5 variables that may appear in a question. They might not. If you have 3 of these and you're looking for this one, see, are you with me here? Equation 1 would be a good choice. Okay? If you're working on a problem and it tells you all kinds of stuff, but it doesn't tell you anything about time, it doesn't tell you about the time, and it doesn't ask you for the time, which equation would be the best choice?
4.
Number 4. Does that make sense? So by writing down your givens, and then by referring to this chart, you can figure out which equation to use, like that, without really having to think very much. You may have to do some solving of that equation for the variable you're looking for, but that will tell you which equation to use, okay? I want to do a bunch of practice. Does that sound all right? Okay. So I'm going to give you a couple problems to work on, like maybe 6 or 7, at your own pace, with your partners. I'll put some solutions up so you can see them. And after we get started, then I will come around to stamp homework and things like that as well, okay? So here's where we're going to start. I want you to start on page 53. Number 1, and then number 4. Okay? Then on page 55, numbers 2 and 4. And then on page 58, we're going to do 3 and 4. So that's going to be a lot of stuff to keep you busy. I want you to give them a shot. I'm going to put some solutions up so you can see them. And then I'm just going to come around and help you and answer questions, okay? These problems are not necessarily going to be easy to start, but the more you practice them, the easier they will become. Okay? The more you practice, the better it will be. And again, I want you to talk to each other. Write down those givens, and then talk to your partners about which equation to choose. Help each other out with the algebra, okay? This is not an everyone for themselves kind of class. You and your classmates need to work together to get this stuff, okay? That. Sorry, thank you for catching that. I write these so much that I don't pay attention. All right, so on equation 2, I wrote it down wrong. I apologize. It should be delta x is 1/2 of VF plus VI. That's totally my fault. I apologize for that. So again, that should be VF plus VI times T. That'll make a difference. That plus sign matters. Thank you so much for catching that. I appreciate it. Let me know if I make any other mistakes. I do make mistakes now and then. It's true. So I'm going to go through a conversion real quick. I will tell you that I never trust myself to just be like, you just do this, right? We've talked about conversions a little bit, right? Okay. If you're converting from hours to seconds or seconds to hours or minutes or da-da-da-da, I always, always, always would encourage you to write it down very, very clearly and carefully. I'm going to go to page 53. So you have a speed, so you don't have to follow along with this, but you might want to, of 23.7 kilometers per hour. Let's go ahead and just convert it straight to meters per second since we're doing it. Does that sound okay? Okay. So if we're going to do this, and I can't remember if we did this kind before, but this is how I would convert it. I'm going to start with 23.7 kilometers per hour, and I'm going to write way over here that I want to convert it to meters per second. And you may remember from 3rd grade or from preschool or whenever you learned your multiplication, because you guys are smart, so I don't know when it happened, but you can always multiply by 1, right? And it doesn't change the value. So I'm going to multiply by clever factors of 1 that will help me get to where I need to go. If I want to convert from hours into seconds, how many seconds are in an hour?
60.
Careful though. Yeah, so there are, you know what I'm saying? I do that because a lot of people gut feeling say 60. It's like, oh, we have to think about that. So you can either do 60 times 60, which gives you the 3,600, or you can write it out one step at a time. Either way is fine. If I write it out one step at a time, I'm going to say 1 hour is equal to 60 minutes. Are you with me there? That's a value of 1. And I'm going to do it again. 1 minute is equal to 60 seconds. So I did 2 things here that are important. I put my hours on top. Why did I put my hours on top up there?
Cancel out.
To cancel with the hours on the bottom in the original part, right? And then I'm also converting from hours all the way to seconds. So my minutes are going to cancel as well. Is that okay? So that's going to give me something. So far I've got kilometers and seconds, but I want meters and seconds. So I'm going to ask myself, okay, kilometers. How many meters are in a kilometer? How many? 1,000. 1,000 meters are in a kilometer. Where is the kilometers going to go? Is it going to go on the top or the bottom? Bottom, why? Cancel, right? So that's going to be 1,000 meters in 1 kilometer. Kilometers are gone. And so now if I follow this path, I'm going to get something in meters per second. So I'm going to take 23.7, divide by 60, multiply by 1,000, and that will give you the value in meters per second. Does that make sense? Yes? No? Questions? Okay. I'll let you keep going.